Let T from R2 to R2 be a transformation that rotates each point in R2 about the origin through an angle theta with counterclockwise rotation from a positive angle. Find the standard matrix of T. So, to get us started here, I think it's nice to consider a geometric interpretation or to sketch what is going on. So, we have a unit circle here because we're thinking about what are these elementary vectors, e sub 1 and e sub 2, being mapped to. So if you have graphing paper, I encourage you to use it. Otherwise, try your best. So here we go, and label. So here is our circle, our unit circle, for the most part. All right, so we have our elementary vectors. So we have our elementary vector, e sub 1. So that has the components 1, 0. And we have the elementary vector e sub 2. That's our elementary vector e sub 2 with the components 1, 0. So these vectors are being rotated in a counterclockwise, or they have counterclockwise orientation from a positive angle. So from the elementary vector e sub 1, this is rotating in a counterclockwise direction. And it's going to some point on our circle, and that's our job. What is this being mapped to? What are the components of this vector? And we have the same thing for the elementary vector e sub 2. This is being rotated in a counterclockwise direction from a positive angle, and our job is to determine what is this being mapped to. Now, we should be careful here with this second vector. Let's just make a note that this second vector, the elementary vector e sub 2, is being mapped to some point in quadrant 2. So that implies to us that this x sub 1 component is going to be negative. So we'll keep that in mind as we proceed. Now, how are we going to find these points? Well, we can use right triangle trig. If we think about in quadrant 1 here, this e sub 1, look at how if we drop that terminal point down, we create a right triangle. The same thing with this elementary vector e sub 2. From the terminal point of our vector, if we drop this down to the x sub 2 axis, we create a right triangle. So we'll use right triangle trig here to find the components of each one of these vectors. So we'll call this case number 1 and case number 2. So case 1. So to help make this extra clear, let's take that right triangle off. So here is that right triangle from quadrant 1. So here is our angle of concern. Now this opposite side here is x sub 2. The length is our x sub 1, and the hypotenuse of this right triangle is 1. Now, using a little right triangle trig here, we know that this is the opposite side. We know that this will be the adjacent side, and that 1 is the hypotenuse. Now, here we go. We, of course, know that sine of theta, using a little SOHCAHTOA, we know that sine of theta is the opposite side by the hypotenuse side. So we have the opposite side is x sub 2, hypotenuse is 1. Oops, we did it. There's your x sub 2 component. Now we know by SOHCAHTOA that cosine of theta is defined as the adjacent side by the hypotenuse side. So the adjacent side here is x sub 1, hypotenuse is 1, and again, oops, we did it. Woohoo! So we can see here that therefore your elementary vector e sub 1 maps to the vector x sub 1, x sub 2, which we're now defining as x sub 1 equals cosine of theta, and x sub 2 is sine of theta. Beautiful. So there's the first part. Now we need to do the same thing here, but with case 2. So case 2 has a different right triangle, but the same idea. So taking that right triangle, blowing it up a little bit. Here is our right triangle from quadrant 2. There's your right angle, and there is our theta of concern. Now again, keep in mind here that this vector is in quadrant 2. So your x sub 1, this length here, is negative because we're in quadrant 2. Hypotenuse is still 1 because we're working with the elementary vectors. And this length here is our x sub 2. And again, using that right triangle trig, using that theta of concern, we can see that this minus x sub 1 is the opposite side. That x sub 2 is your adjacent side length, and 1 is the hypotenuse. So, using SOHCAHTOA, we know that sine of theta is again your opposite side length by the hypotenuse side length. So opposite is minus x sub 1 all over the hypotenuse, which is 1. So this is letting us know here that x sub 1 is going to be minus sine of theta. And again, using SOHCAHTOA, we have that cosine of theta is equal to adjacent by hypotenuse. So our adjacent side length is x sub 2 by the hypotenuse of 1, which equals x sub 2. Woohoo! So we can say here that therefore the elementary vector e sub 2 maps to the vector with the components x sub 1, x sub 2, where x sub 1 is minus sine of theta, because again, this is in quadrant 2, and x sub 2 is equal to cosine of theta. So we have everything that we need. And let's make one final love note here to ourselves. That when we say that this elementary vector, e sub 1, is mapping to this vector, another way to say that is that the image of the elementary vector e sub 1 under the action of our transformation t is equal to the vector with components cosine of theta, sine of theta. And the same thing with case 2, saying that the elementary vector e sub 2 maps to this vector. Another way to say this is that the image of the elementary vector e sub 2 under the action of our transformation t is equal to the vector with components minus sine of theta, cosine of theta. So, with this in mind, we are ready to state the standard matrix A of our linear transformation. So the standard matrix of our transformation T, now we know by definition, is a matrix A whose column vectors are the images of the elementary vectors, which we just found. So we have that this standard matrix of T is the matrix whose first column vector is cos of theta, sine of theta, and whose second column vector is minus sine of theta, cosine of theta. Woohoo! So this is our beautiful final answer here. This is the standard matrix of T. And now this matrix also goes by a special name. This is also sometimes called the rotation matrix. This is our rotation matrix and beautiful final answer.